let's take the 2 degree of freedom system that looks like this. So we have mass 1, we have mass 2, we have K1, K2, and K3, right? So using modal analysis, we want to show the temporal response for our entire system for the first 20 seconds. Right, so we want to find x of t for the first 20 seconds. That's our goal. So first, we're going to use the full modal reconstruction to rebuild this, and then we'll do it with just half the modes. So how many modes is a system going to have? Yeah, and how many degrees of freedom do we have? 2, right? So we're going to have 2 modes. So first, we're going to rebuild it using both modes, and then we're going to rebuild it using just one mode. That makes sense? So it is kind of toned down from what we were talking about before, but that way our matrices are something we can actually write. And then I've got some initial conditions here, right? So F1 is equal to F2, which is equal to 0 Newton. So we're not going to force it, right? M1 is equal to 10 kilograms. M2 is equal to 1 kilogram. K1 is equal to 30 newtons per meter. K2 is equal to 5 newtons per meter. And K3 is equal to 1 Newton per meter. And let's go with x1 of 0 is equal to 1 millimeter. And V1 of 0 and x2, well, let's just go all others are 0, right? So that's the only other. That's the only one we care about. We don't need to write 0 a bunch of times. So we've got free or forced vibration. Yeah, we're not forcing it. So free vibration, right? We're gonna move M1 a little bit, and then we're gonna release it. So pretty simple free body diagram here. We've assumed that x2 displaces a little bit more than x1. Again, you could do the other way; you'd get the same values. But let's go ahead and just write these equation of motions. In the interest of time, M1 x double dot of 1 plus K1 plus K2 x1 minus K2 x2 is equal to 0. Oh, shoot. No, it's plugged in. It's charging. It's warm. I don't know. And then our second one is M2 x double dot of 2 plus K2 plus K3. That's all multiplied by x2 minus K2 x1 is equal to 0. Right, so in matrix form, this is going to become M1, 0, 0, M2. X double dot of 1, X double dot of 2, pretty simple. So in our x1 term, we've got a k1 plus k2 in the top left, so that's going to become k1 plus k2, and then we have a minus k2, and then down here we have another minus k2, minus k2. Sorry, our minus k2 times x1, so that goes in the left corner, and the right corner is going to be k2 plus k3. x1, x2. Is equal to 0, 0. Right, and then we can also do our initial vectors. So we have x vector of 0, that's our initial conditions, equal to 1 and 0. And x vector of 0 is equal to 0 and 0. That makes sense? Pretty good? Okay. So we can solve our eigenvalues using our generalized eigenvalue problem. Right, and that's going to be K matrix of eigenvectors is equal to lambda mass matrix of eigenvectors. Right, so Python or MATLAB or MathCAD or something, Mathematica, something gives us lambda 1 is equal to 2.73. That's our eigenvalue, correct? And our eigenvector, V1 vector, is equal to 0.546 and then 0.837. That makes sense? You get a value for a value and a vector for your vector. Lambda 2 is equal to 6.76. Let's just drop it there. And your second eigenvector is negative 0.15, 0.98. Right? Okay. Eigenvectors, eigenvalues to natural frequencies. Square root. Super simple, right? So omega 1 is equal to the square root of lambda 1, which is equal to 1.65. What are the units? Radians per second. All right. So because we use the generalized eigenvalue approach, how do our eigenvalues relate to our eigenvectors? Sorry, how do our eigenvectors relate to our mode shapes? Do we have to do the m to the negative 1/2, or is it just I don't watch ads. Ads are a tax on the poor and technically illiterate. Okay, so for our eigenvectors and eigenvalues, for our eigenvectors, how do they relate to mode shapes? When we use a generalized eigenvalue solution, do we use the inverse of the mass matrix? Do we multiply it by that?
Inverse square.
So we do that when we have a mass normal, when we solve the eigenvalues with the mass normalized stiffness matrix. But here we solve them with a generalized eigenvalue problem. So our eigenvectors are our mode shapes, but they just have to be scaled. Does that make sense? So we're going to have, again, this is where it gets a little confusing. v1 vector is equal to v1 vector alpha. And we say it like that because the information inside the vector does not change. Even though it's different numbers, the information does not change. And that's going to become the same as before, right? So 0.54, 0.83 alpha. And omega 2 is equal to the square root of lambda 2 is equal to 2.60 radians per second. And v2 vector is equal to v2 vector alpha, which is equal to 0.15 to negative 0.98 alpha. Okay, so we have to find a value for alpha, right? So we want to normalize these with respect to the mass matrix, which is what we do in the generalized eigenvalue problem. So for that case, we're going to have a 1, because we want all of our, this is all for plotting, right? So we want everything to equal 1, but it has to be mass normalized. So 1 is equal to our v1 vector transpose, if you deal with transposes on vectors, m v vector 1. That makes sense? So again, you can see how we're mass normalizing, just like we did before. So this becomes go ahead and insert v1 is v1 alpha, and v1 is v1 alpha. You guys agree with that substitution? Right? You're going to end up with 1 is equal to alpha squared multiplied by, so for v1, we have 0.54, 0.83, and then our mass matrix, which is 10, 0, 0, 1. And then our matrix, but not transpose, 0.54, 0.83. Can you solve that for alpha? Right? What is this? What does this whole block give you? What's the shape of the output of that value? Is it a matrix? Is it a scalar? Is it a vector? Yeah, scalar, right? So you have a scalar. I'm just going to put an s there, and now you can solve for alpha squared. Pretty simple. You know, 1 divided by the square. So it's alpha is equal to the square root of 1 divided by s. Pretty simple. Okay, so for alpha 1, I got 0.52. All right, so I do the exact same thing for alpha 2, but my vectors change, correct? My mass matrix stays the same, but my eigenvectors change. So alpha 2 is equal to 0.91. Right? And now we can just apply these to our vectors, to our eigenvectors, and we can build our modal matrix, right? So our modal matrix P is equal to our updated alpha values. So let's write that V1 alpha, V2 alpha. So that's going to be 0.284, 0.435, negative 0.137, 0.900. That makes sense? And if you look at this, how does this relate to our original eigenvectors? Before you had eigenvector 1, and 2 is not quite double, right? And then you pretty much have 0 and 1 here. And then once we scale them, right? So this one's not quite double, but pretty close, and you pretty much have 0 and 1. That makes sense? So, but now they're orthonormal, or now they are orthonormal, which is important. Okay, so now we need to check, right? Boy, do I hope this works, because we need to verify this equation, right? Because if we don't have an I there, then our entire assumed equation of motion falls apart. That make sense? So that's pretty easy to do, though. So let's check. So check that P transpose MP is equal to I. And I have that as 1 negative 2.7 e to the negative 16 negative 2.7 e to the negative 16 1. All right. Are those zeros close enough to 0? Right, that's what Python gave me. That's a rounding error. So there is actually a function in Python that you can ask, is this identity? And if you just type that in, that will return no, right? And MATLAB has the same thing. Actually, MATLAB might. There's like a value to where you set your 0, because computers don't really do 0 very well. But that's equivalent to 0, right? So that's good. So I'm happy with that. We'll give that a green check mark. So, yeah, go ahead. Or is that an echo of my own voice? Dang it. They've all fallen asleep anyways. So.
I can still hear you.
Okay, thanks. Someone's still awake. And now they're typing mean things about me, but I won't be able to read them, so that's fine. Okay, so now we trust P, right? Which is our modal matrix. So let's use P to go into our modal space, right? So let's take that trip on that magical animal thingy into the modal space.
Professor Downey, your computer screen is black on mine.
Oh, is it black on anyone else's?
Yes.
Yep. Yeah, that's unfortunate.
It just happened like 2 seconds ago.
Let me close. Okay, can you see anything now?
No.
Still black?
Yeah.
Okay. How about now?
Now it's white. There we go. Now your screen's showing all the blackboard. Yeah, there you go.
Okay, perfect.
All good.
Thanks. So now we trust P, right? So we can go ahead and solve that equation. Again, if we look up at our equation of motion in modal space, it's this. I'm going to see if I can copy that. So this is what we had before. Right, so let's go ahead and break this out a little bit. So this is going to become q vector of acceleration as a function of time is equal to omega 1 squared 0, 0, omega 2 squared qt vector equal to 0, 0. Right? Because we're not forcing it. And that's our equation of motion in modal space. So we can break this out into one row. So let's just look at I, right? So again, we have qi, not a vector, the function of time. That's one coefficient, participation coefficient, but it varies with time. So what mode, the amount that each mode participates varies through time in the system. Plus omega I squared. Well, that's good. We know in omega I, qi of t, that I is subscript. So we don't know that is equal to 0. And we have two modes, so I equals 1 or 2. So you can build that equation two ways. That is an ordinary differential equation. And do we have a solution to that? Right, we have a solution to that. So we have qi, dang it, qi of t is equal to qi initial cosine of omega I t plus qi naught dot over omega I sine of omega I t. That's pretty simple, right? So we have everything we need there except qi naught and q dot I naught. But we can get those. So q vector, which is just both of our initial conditions at time 0 or subscript naught, is equal to p transpose mass matrix x vector at time 0, which is equal to 0.28, 0.43, negative 1.37, 0.90. Am I doing that right? Am I transposing that p? Yeah, my 137 is in the other place. Times our mass matrix, which is just 10, 1, and zeros. 10, 0, 0, 1. Times our x naught, which is going to be 1, 0. That's going to be 2.846, negative 1.378. Right? So now we have values for q naught. Okay, for q naught. What about q dot naught? Just same thing, right? Q dot naught of 0 is equal to p transpose m x vector dot of 0 is equal to that same thing, but what's important here is we're going to have zeros. Same. That's my symbol for same. We're going to have zeros on our initial conditions. So what is our resulting matrix going to be? Just 0 and 0. Right? That makes sense? Okay. So now we can go ahead and get functions for Q1 and Q2. So Q1 is equal to Qi naught, which is going to be 2.846. Does that make sense? This and this. So 2.846 cosine of omega I, And what's omega I1? At 1.65. That sound right? And then t is a variable, so t is going to stay. Plus, what happens to the second term? What's qi? What's qi or q1? Q dot 1 initial. What's this value? 0, right? So it just falls off. Nothing. So there we go. We have a q1. Now we have a q2 is equal to negative 1.378 cosine of 2.6t. So these are pretty helpful. These tell us how much each mode participates at a given time. And we know the modes. So now it's just an issue of summating them up, right? These are our time-dependent participation coefficients. All we have to do is multiply these by the modes, right? But that gives us our response in modal space. We want our response in the physical space. Well, then we have to use P, right? So we have the solution which we've given before, x of t, and that's a vector, is equal to our modal matrix P times our q vector of t. Do we have the q vector of t? Right? That's these two, just put into a vector. So q1 on top, q2 on bottom. Okay, and I'll write this out because whatever. So that gets us x vector of t is equal to 0.28, negative 1.37, 0.43, 0.9. I'm dropping some significant figures. Times our vector, which is 2.846 cosine of 1.65 t, and negative 1.378 cosine of 2.6 t. Right? So it's going to be, so x1 is going to be 2.8 times 2.84 cosine, and plus negative 1.37 times 1.38, right? So 2.8 times 2.8 cosine plus negative 1.37 times 1.37 cosine of 2.6. So that gets you x of 1 is equal to 0.808 cosine of 1.65 t plus 0.189 cosine of 2.6 t. Do the same thing for x2. x2 is equal to 1.238 cosine of 1.65 t minus 1.24 cosine of 2.6 t. So that is the reconstruction using both of our modes. Does that make sense? So let's go ahead and take a look. Copy image. Okay, so So here's the displacement for that system, right? We have x1, which has a pretty nice displacement. You know, there's a little bit of ripple here. You can see that it's interacting with that cosine. And then you have x2, which is our second mass, which has a much more complicated shape, right? And you can start to see, you know, some of the second mode in here, right? So the first mode is going to be them moving together in phase, and the second mode is them going to be moving apart. Right? Is that what we got? I should actually not say things, but yeah. So the first mode is actually them moving together, and the second mode is them moving apart, or one staying still and the other one kind of moving around it. And they're not perfectly spaced like the last ones, where they're perfectly apart, perfectly moving together and perfectly moving apart. And why is that? If you think about the system. Remember that example we had where like the blue lines and showing you what the blocks did? Remember that picture? Anyone? I spent like hours making it. So hurt. Yes? No?
What do you mean by blocks?
Is that a you don't remember? All right, remember this picture? Our first mode are the two blocks moving together, and our second mode are the blocks moving apart. Right? Why is that not the modes we have here? Here we have modes of 0.4 and 8.3. So they're kind of moving together, but they're also moving apart a little bit. And here we have modes of negative 0.5 and 0.98. You can tell they're trying to move apart, but like it's skewed. Both of these are skewed to one side. Why is that?
Because the weights are different.
Yeah, it's because the weights are different. So in the last example, our two masses were equal, right? Here we have a mass that's an order of magnitude larger than the other mass. So which is why we want to, you know, one of the reasons we mass normalize eigenvalues. Does that make sense? Okay. You know, the mode shapes of things like poles and cantilever beams look really pretty because it's a continuous system of mass. But other systems get real complex real quick. So here we are using both of these systems. Okay. What if we want to build, so we went to the modal space, we did our conversion, we came back. What if we want to drop a mode in the modal space? I just want to rebuild this using just the first mode, right? I just want the fundamental movement. I'm not concerned about the little jumps, right? I just want the general idea of what my system is doing. How do I do that? That's a clever idea. I really like it. Sounds hard. I don't even know if it would work. But I like the thought process. But let's maybe move forward a bit in the math, right? We have two participation factors, Q1 and Q2. Let's just take Q1. That makes sense? And we can drop Q2. How about that? Right? So if we think back to this equation that we wrote, here, we just want what's in green, except here we're just taking the first one, right? But we're taking some amount of our participation coefficients multiplied by our eigenvectors, right, to rebuild our x of t. So let's go ahead and do that.
So when you say drop, are you just literally multiplying by 0?
Sure.
Summation?
Sure, I'm just not copying into your code. So we have x of t is equal to, in this case, we're going to have Q1 oh, sorry. No, we want to go to our modal space. We have to think modal space. So we have x at t times p, which is our modal matrix, which gets us out of the modal space, right? And so before we had q vector, which we're still going to have. It's a vector of 1 in this case, but we're going to call it q truncated. Right? So we don't have all that information. So our p is going to be the same, 0.284 negative 0.137, 0.435, 0.900, right? But now what is q truncated? We're just going to have the first mode, right? Or we're just going to have the response associated with the first mode. So we have 2.846 cosine of 1.65t. That makes sense? But wait, there's more. So this is really cool because just because we take the first coefficient, right, I'm going to multiply 0.284 times 0.86, and then I'm going to do 0.35 by 286. So I still get a displacement for x1 and x2, right? So I have x1 is equal to 0.808 cosine of 1.65 t, and x2 is equal to 1.238 cosine of 1.65 t. Right? So I have a simplified response, but I'm still going to get a response at every degree of freedom. Make sense? So and all we did was drop off those terms. So let's go ahead and pull in our next plot. Does that look like a simplified displacement of the previous plot? Right, we still have the natural frequency. You know, it's not displacing as much. Before it was going up to like 2.5, and now it's going up to like 1.5. But you know, they're mostly in phase, right? And actually, you can kind of see how when you get rid of the second mode, this truncation of the signal is just an addition of the second mode, right? You know, the second mode or the first mode here is kind of counteracting. That's why we have a lower value. But it's generally a simplified approach, right? So this is a relatively common, not relatively, this is a somewhat common approach in control systems, right? It gets very hard to kind of predict a time series control of a structure, so you want to truncate the structure. Granted, you're probably not going to go to the first. You're going to go to the first 5 or something, but this problem is long enough to walk through without writing huge matrices. So, okay, what about our time series? So this gets a general idea, right? But it misses the finer components that the second mode contributes. So let's look at the time series response of Q1 and Q2. right? So here we have Q1 and Q2. We have participation. There's not really a unit associated with that, right? It's a scalar. And you can see that at different times you have Q1 and Q2 are contributing differently, right? So this is how much, mode 1 is contributing quite a bit here, and then mode 1 does not contribute at all at about 1 second, right? And it's pretty much a mode 2 response, which is why you get this very complicated kind of time series response.